In this video, I'll be starting Chapter 5. Now, moving forward, I'm going to break up every chapter into smaller, kind of bite-sized chunks of the information. So hopefully that makes it easier for you to kind of take in and digest the information, and also hopefully it makes it easier for you to go back afterwards when you're studying and find whatever material you're looking for. So with that, today, this video is going to cover a few basic terms in the beginning, and we go over one key concept, and that'll be it for this video right here. So, starting with Chapter 5. Chapter 5 is about thermodynamics. Thermodynamics is the measure of the final state of a chemical reaction. So the study of chemical reactions can kind of be broken up into two different concepts. One is thermodynamics, and one is kinetics. Kinetics talks about reaction rates, so how fast a reaction goes, how many steps it goes through to get from the initial reactants to the final products, all of those kind of things. Thermodynamics doesn't care about any of that at all. All thermodynamics cares about is that no matter how long it takes for a chemical reaction to happen, no matter how many steps it has to go through, whenever it gets to its final state, what does that look like? So that's what we're going to be talking about in this chapter. Now, first, again, I want to define a few basic concepts. So one thing I'm going to define is work. So you hear this word all the time, but at least in scientific terms, what is work? Well, it's the ability to move matter some distance. So work, represented by W, equals a force times distance. So you have to apply a force to a certain amount of matter, and it has to move some distance. It could be an extremely minuscule amount, but it has to move at least a little bit. That's work. Now, energy is defined as having the capacity to do work. And energy can be further broken up into either potential energy or kinetic energy. Potential energy is stored energy. And along the lines of chemistry, potential energy is stored in chemical bonds. Kinetic energy is the energy of motion. Now, we haven't really talked about it much, but molecules are always moving. Nothing is ever stationary at the molecular level. They're constantly vibrating or rotating or moving around, and that is the kinetic energy in a chemical reaction. And one last term is temperature. Now, a lot of times when people hear temperature, they just think it's just, oh, that's how hot something is. But that's not actually true. What temperature measures is it's the average kinetic energy of every particle in a sample. Alright, now there will be more definitions throughout the chapter, but I'm just going to start with this video with those several. Now I want to talk about one key concept, and that is something known as heat capacity. And a slight variation of it as well, which is the specific heat capacity. Now, heat capacity is the amount of energy required to raise a sample (1 degree Celsius). Specific heat capacity is extremely similar, but it just takes mass into account. So the definition for specific heat capacity is it's the amount of energy required to raise 1 gram of your sample 1 degree Celsius. Now, the equations to represent these are Q equals C delta T for the heat capacity, and for the specific heat capacity we have Q equals M C delta T. Q is your heat, which is also your energy. So heat is just a form of energy, and there are a bunch of different forms that energy can take on, but for the sake of this chapter, the only kind we'll be talking about is heat energy. So heat and energy are synonymous, at least in this chapter. They mean the same thing. This C variable right here, that is your heat capacity. This triangle, that's actually the Greek letter delta, and that means a change in something. So this delta T is actually one variable together, and that represents the change in temperature. Those three variables are effectively the same over here. Q equals the heat. C is now your specific heat capacity. And your delta T is your change in temperature. The only difference is M represents the mass. So heat capacity and specific heat capacity are going to be constant for a material. So if you have, for instance, water has its own specific heat capacity, and that's never going to change, at least for that state of water. It can change between gas, liquid, and solid. But the heat capacity, or the specific heat capacity of water, is going to be different from between that and wood, for instance. Wood has its own specific heat capacity. Every material does, but as long as you stay within the same material, the heat capacity remains the same. Now, there are first I do want to talk about, units. So units for heat, there are two units that you want to know. One is joules, represented by a capital J, and the other is calories, represented by CAL. So they're both just different units for heat. Sorry, let me get that on the screen. There we go. And the conversion between the two is that 1 calorie equals 4.184 joules. In this equation, mass needs to be in grams. So the units for the heat capacity are going to be joules per degree Celsius. And down here for specific heat capacity, our units are joules per gram degree Celsius.